I'm very pleased to welcome Jake, who will give a talk about domain-specific languages for microservices.
Hi, I'm Jake. I work at Twitter. I want to tell you about domain-specific language for microservices. I want to start by motivating the problem I'm trying to solve a little bit. So, actually, let me back up. I'm going to tell you about a system that we built at Twitter for serving microservices using the Scala-like language. And I want to start by motivating why we might use this kind of thing. Okay, Twitter is a large software system with hundreds of people working on it. How can we organize this system so that these hundreds of engineers can avoid wasting their time? Let me talk about a few ways that we've tried that waste a lot of time. So long ago, Twitter had started with a monolithic service. So the Twitter application was one code base with a whole bunch of people working in it. Fortunately, it wasn't hundreds and hundreds of people at that point, but it was a lot of people. And a big problem that this had was that everyone was stepping on everyone's toes, right? So we were all sort of working in one code base. There was one deploy process for this whole time. And it was difficult to get anything done. Wasteful. There were some good things, though. So a lot of things were taken care of for you. You're working in one source code repository. There's a deploy system and a deploy team that does deploys for you. There's a whole bunch of logging and stats infrastructure. And the sort of framework that you're serving requests out of is a shared resource, right? So there were some good things about having a monolithic service. Nonetheless, Twitter was like, this problem of people stepping on each other's toes is too bad. We should break up into lots of little services. And that's what we did. And now all these things that you sort of got to share over here are now replicated across many different services. And this is really good for autonomy. Different teams that own these services can independently deploy their things. It's bad for leverage in that there's all this stuff you have to redo for each service. So this is just a capsule summary of the problem we're trying to solve with this system. If you care to look at the video of my Strange Loop talk, I go into a lot more detail about how this is played out. Okay, so what we have built is this thing called Strato, which is a platform for microservices. So it's sort of a shared service that has gives you a bunch of leverage. You get a bunch of things for free, and you write your microservices as configuration within the system. And you might ask, what is different about this from the picture of the monolithic system? What's different is that we've sort of thought hard about how to retain teams' autonomy in this environment. So rather than everyone stepping on each other's toes in a single code base, we have a bunch of well-defined interfaces between different configured microservices in the system. And we've kind of separated out the service platform-level deploy from the configuration deploy. So the turnaround time for people working in the system is much faster. Okay, so that's the motivation. So why would we built a new language for this? Sorry, I didn't make that clear. The business logic in these things is written in this DSL, which is called StratoQL, which I'll be talking about. Why do this? Why not just use Scala or something like that? A really big motivation is sort of control and operability of the shared platform. So there's a team that owns this service and has to run it, and it's really valuable to have a really small, simple implementation that we understand well. We'd like to be able to limit supported language features, so we don't really want to admit any old Scala code into the system. We want to have pretty tight control over it so that people don't send us computations that are going to be very expensive or something like that. We'd like better control over exactly how code gets loaded into the system. You can imagine doing something with bytecode loading or something like that, but that doesn't give us tons of control. And another important point is that we rely really heavily on types as runtime objects. So these microservices that are running in the system, again, have typed interfaces. We want to be able to generate binary serialization and stuff like that from these types. That's not as easy to do if you're sort of loading from something. And another reason is that we're going to have some domain-specific features. And what I mean by this, all of these services communicating at Twitter are talking thrift to each other. I forgot. Can I get a show of hands? Who knows what thrift is? Who knows how it works? Okay, I will spend a couple minutes just giving you background on that. Another domain-specific feature we want here is sort of transparent concurrency. So if people are familiar with Haxel, Simon Morley's thing a few years ago, we want to be able to express computations that talk to a bunch of different services, aggregate results, without having to worry too much about all the details of blocking and asynchronous. Okay. So let me give you some background on Thrift RPC because it motivates some of the design decisions in this language. So Thrift has this IDL for defining interfaces between services. And it has a simple type system. It's got primitive types, a few sort of built-in collection types, structs, like think of those as records, unions, variants. And the typical use of Thrift is that you have lots of independent communicating services which are not compiled at the same time. They may be upgraded at different times. And so communication between these things is effectively structurally typed. It doesn't really make a lot of sense to talk about nominal types when everyone is deployed separately. Thrift extends this idea of structural typing a little bit with this idea of compatibility between types. So you may, for instance, if you have a record, you can add an optional field to it. And that's sort of compatible in both directions. So if you send a record without the optional field and your receiver is expecting it, well, it's optional, so it's okay not to have it. If you send the optional field, if you fail to send the optional field to someone who is expecting it, again, that's optional, it doesn't matter. So this is kind of how interfaces evolve in a complicated Thrift system, is you rely on this compatibility so that your deploys aren't tied together and it's not too hard to do. This might strike you as incredibly unprincipled and very sloppy. It is, but this is how we do it. So, okay, so now I want to tell you a little more about startup code. So this DSL looks a lot like a very stripped down Scala. So it has sort of the Scala core functional pieces, tuples, records, variants, pattern matching functions, but it is not at all object oriented. We don't have traits. We don't have any of Scala's fancier types. In particular, we don't care at all about interoperating with Java, so I understand, well, my presumption is that a lot of type system aspects of Scala were motivated by interoperability with Java. We don't care about that, so we don't do that. In contrast to Scala, this language is structurally typed, again, because we're talking about lots of different communicating systems. This is a good fit. And we have kind of native support for Thrift data. So if you've used an RPC system, it's pretty typical to write down your RPC interface and then compile out stubs in different languages that want to talk to each other. This doesn't, there's always some little impedance mismatch there. It doesn't always work that well. But because we're really focused on this domain, we just sort of build the Thrift type system directly into our type system. So any Thrift type is also a StrataQL type, and you can sort of work with it directly. You can pattern match on it directly. And again, we have this idea of transparent concurrency, so you don't have to think too much about asynchronous. So let me give you an example of that. Okay, another show of hands. How many people use Twitter here? Okay, good. Last time I asked that question and talked like this, people were like, I've never heard of Twitter. So it's a few years back. But, okay, so what we want to do in this little fragment of code, this is kind of contrived, but it's pretty representative of the sort of thing that we do all the time in Twitter. We want to assemble some tweets from a timeline by consulting a bunch of different services. So the parts here that say, so user by name is a service that represents users looked up by name. It returns a Thrift object containing user. So the first thing we're going to do here is fetch a particular user by name. We get back this user object. And then we're going to do a pattern match on it. So this is kind of the least Scala-looking part of this. But I guess maybe some MLs have pattern matching like this. So we just want to extract the user ID field, possibly from a very large Thrift object. That's very typical that we have these huge objects with dozens or sometimes hundreds of fields on them. So it's really convenient to be able to match out the part you want. And then we're going to call another service, timelines by user ID, which is going to give us a bunch of tweet entries, which consist of a tweet ID and an author ID. And then for each of those, we're going to consult a couple more services, which will look up the tweet object and the user object for those IDs. And we'll put this all back together into a sequence of tuples of user text. So I guess what I want us to notice about this is that we are making a bunch of asynchronous calls, and that's not reflected here at all. We're not dealing with features or anything like that. What else should we notice? Well, actually, so let me just move on to what this is going to look like in terms of RPCs. So, sorry, let me back up. We have a bunch of entries in this timeline. We're going to look up tweet text and usernames for each of them. So it might look like we're making a separate RPC call for each of these. But much like Haxel, the way this works is that we can sort of find all the calls we're going to make and batch them together so that we can make a single boosted call, and that's a lot more efficient. It makes this actually work well. So this is how the actual execution plan of this computation happens. We consult one service to get the user object for a username. We consult another service to get the timeline for that user ID. These thick arrows are supposed to indicate fanning out a bunch of items. So this is sort of a batch call to get the tweets for a bunch of tweet IDs, and a batch call to get the user objects for a bunch of user IDs. And then that comes back together when these asynchronous computations have completed, and we can compute the final response. So that's how that goes. Okay, so I'm going to talk a little bit about the implementation, the type checker, and how we compile it. Show of hands, are people pretty familiar with the local type inference paper from, the Scala uses this, I assume everybody, okay. So I will just kind of breeze through this part. And I'm nervous here because I'm an industry person who is interested in programming languages, so if I totally botch this, please don't be too disappointed. Okay, so local type inference. The big idea here is that, well, there are two big ideas. One is this idea of bidirectional type checking. When we have an expression and we don't know the type, we can synthesize the type from the parts of the expression. And when we do know the type and we want to check that an expression matches that type, we can kind of break down both the expression and the type usually to sort of recursively subdivide the problem. This turns out to be really nice for error messages, as I'm sure you know. This gets you much better error messages if you can stay in checking mode. Okay. The other big idea from local type inference is how you do inference of type parameters to polymorphic functions. And the way it's given in the paper is that you synthesize the types. Sorry, I'm going a little faster. So let's look at this example. We have this function f with a couple of type parameters, and we want to figure out what they are in an actual application. So we synthesize types for the argument expressions, and then constrain these type parameters by the argument types that we got from synthesis, and finally instantiate them to be most informative, which I'll get up in the paper. Okay, so how does this work in StratoQL? Well, we basically follow this pretty closely with some extensions. So one of them, just like Scala, a weakness of that original formulation is that if you're using anonymous higher order functions, synthesizing types for those doesn't work very well. We can't synthesize a type for an unannotated function like that. So just like Scala, we check it instead with an environment of constraints and try to refine those constraints as we do the checking in order to finally come up with the final types. So that's just like Scala, I think. Another thing we do that's a little bit different, so let's see, I was talking before about thrift data and optional fields. So it's pretty typical for, I was talking about the evolution of these interfaces between different systems. It's quite typical for a thrift signature to sort of grow over time, where it's like, you want to add some new functionality, so you need to add a new field, and typically you want to have compatibility with some fielded system, and so you do that in this backwards compatible way. So it's pretty typical to add default values or optional fields, things like that. We would like to be able to make use of these defaults in StratoQL code. So if you write down a record and you try to use it as another type that has some defaulted fields, you'd like to actually incorporate those into the record you wrote down. So it turns out to be really convenient in this checking mode of the algorithm to sort of do conversion of various kinds. And so one kind of conversion that we do is to fill in defaults where they exist. So here I've written down an incomplete record for the type. I've just given x equals 7, but when we check this expression against this type, which has a default value, we can just fill in the y field. And so that's something that happens as part of the checking process. And this has turned out to be a super useful facility for a million things, and we use it all over the place to do various somewhat unprincipled conversions that are very convenient. So that's how it works. Okay, let me talk about another extension of this that we do. So, so asynchrony and concurrency is kind of behind the scenes in this language, but sometimes we need to know about it. So there are a few situations where we want to know if an expression is synchronous or asynchronous. So we also compute an asynchrony effect along with type checking. So that's just a flag saying whether it's synchronous or asynchronous. And if you're familiar with effect systems, it's typical for the function type to carry the effect with it. So that's what we do, of course. There's a very natural notion of sub-asynchrony. You can treat a synchronous function just like an asynchronous one. And we do, in the same way that we did the local type inference of polymorphic type parameters, we can do the same thing for asynchrony, so that we can have functions which are asynchrony polymorphic, such as map. So you want map to be asynchronous exactly when its argument f is asynchronous. Okay, I see that I have a little more. I don't know if I will focus in 5 minutes. Let me briefly breeze through how we compile this thing. So we have a library at Twitter called Stitch, which is a lot like the Axel library. It's sort of a monad for doing concurrency. Its interface looks a lot like Future, but we have this ability to batch atomic calls into RPCs that I was mentioning before. One thing we discovered after using this library in a bunch of systems was that the monadic interface does a lot of redundant work. It's pretty typical for, you want to do some computation over a bunch of keys, like a bunch of tweet IDs. You're basically doing the same computation in each one, and the monadic interface redoes a bunch of stuff, because bind is like a little too powerful. It doesn't really capture the fact that this never changes based on the data that you pass it. So we ended up adding an arrows-based interface to this library so that we can kind of capture the static aspects of the computation better. So in contrast to some other uses of arrows, we're not trying to restrict the expressiveness here. We're just trying to identify the static parts so that we can do them faster. So we can compile this language I was telling you about onto this arrows library in a pretty straightforward way. So these red brackets are compilation brackets. So if you have a tuple of expressions, that compiles to an arrow join. We are sort of passing the binding environment through this arrow. So if you bind a variable like this, we have an arrow representing the compilation of E1, and that produces an augmented environment that we pass to the compilation of E2. Okay, so how is this working out? This system is getting a lot of usage on Twitter. I think there's more than 200 microservices running the system right now. It's giving us some interesting extensions. So we built a GraphQL layer on top of this. I don't know if people are familiar with this, but it's kind of a generic web API which we're using in the mobile clients for Twitter. And what's cool about this is that by centralizing all of these microservices, we sort of have we centralize them and put them in a catalog with types attached to them. It's quite easy to generate a GraphQL interface from that. If we had to individually do this for every microservice of Twitter, that would be quite difficult. Another thing we've been working on is an event processing system. So everything I've been describing here is sort of request-oriented, but we have a lot of event processing applications at Twitter, so we're just kind of transporting all this technology into that layer. Okay, so this is meeting our design goals. We've gotten a lot of leverage for people, and for the most part, we've given them good autonomy. They can kind of independently work on these configurations. That's worked out well. But a new language has a really high bar, as I'm sure you all know. The implementation, the documentation, libraries, IDE support, and the fact that this is all happening in a centralized team kind of creates a bottleneck for people. So if they need a new feature, it has to go through this team. So that's been a little bit of a problem. I want to leave you with this thought for the future. So the execution environment that we work in has become really complicated. The execution environment at Twitter is like lots of interacting pieces with really high rate of change. But the language execution model, I think, hasn't changed that much. We still sort of think about compiling executables. I wonder if maybe we should try to co-design our languages and our execution models a little bit more. So that's my thought. Thanks so much for having me. These are a bunch of people who worked on it at Twitter. Do you have any questions?
Questions?
What questions do you have?
Yeah, could you expand a bit on this monad versus arrows? So you went a bit fast.
Oh, sure. I'm sorry. Someone flashed a 5-minute warning at me. My heart rate increased. Okay, so in a monadic bind, right, you get the data that you're depending on as an argument, right? And you're free to do whatever you want with that data. You can branch your computation, of course, but most of the time that doesn't happen. Most of the time you're sort of passing that through in a uniform way, right? So like you're basically just not relying on that data. And I don't know if this is inherent to the interface, but at least in our library, using Biden that way would cause some allocations, cause some computation that was basically repeated for every item in a large list, right? With an arrows interface, you just sort of capture all that once, and you just run down the list applying it without doing any intermediate allocations. Like you don't have to rediscover the structure of the computation for each key. You just sort of capture it once and then apply it a bunch of times. So we benchmarked this, and it was a noticeable performance improvement. I can give you a more concrete example.
You said towards the beginning that interop wasn't a concern for you, which, I don't know, that strikes me as weird because most new languages, like, they get most of their library support because they interop with some language that has far more libraries.
Yeah, that's a really good question.
So has that been an issue, or?
So yes and no. So I think it gets back to what I was saying about trying to limit the capabilities of the language because the team has to operate this, right? So we don't want kind of anyone to be able to link in any JVM library into the system because that puts an operational burden on the team that runs it. We want to just have tight control over that. So you're right that we often have to sort of write wrappers around sort of standard library functionality that people need, but we don't want really for that to be completely uncontrolled. You know, people to link in.
So related to that, how do people write libraries in that language, or is it more used as a kind of like application logic?
Yes, it's used as more of an application logic. So,
okay, so you're just providing a whole set of kind of modules that.
Yeah, that's right. So we have some sort of common functionality that we offer as part of the standard library. If people want to do something really complicated, we typically tell them that they have to write an external service and call it through this thing.
Right.
So, for instance, evaluating a machine learning model, that's something that we're not going to do in process. We want to get that into some process.
All right, let's thank Jake again.